100% fresh, 100% clean. How clean is our air really? Or more importantly, what's science doing to maintain or improve it? Hi, I'm John Watt, and this week I'm taking you behind the scenes to look at what Kiwi scientists are doing to tackle air pollution. Let's head to Auckland waterfront, somewhere down there, to find out about air pollution from the people who study it. NIWA, the National Institute of Water and Atmospheric Research, on the edge of Auckland's viaduct. NIWA are currently gathering data to give us a clearer picture of our urban air quality in an 8-year research program called Healthy Urban Atmospheres, or HUA. Leading HUA are two scientists, Dr. Guy Coulson and Dr. Ian Longley.
Scientists rarely get 8 years to work on one problem. The project is looking at air quality in all sorts of forms. It's looking at what is the hazard to our health presented by air quality, to what degree are New Zealanders exposed to that hazard, and also how can we design our cities so we don't have an air quality problem in the future.
New Zealand being an island in the middle of the ocean, we aren't surrounded by neighbours who are polluting, so we have a situation where any pollution you find in New Zealand is our own fault. So the advantage of being on an island is that it makes it much easier for us as scientists to isolate the individual pollution sources that we're interested in.
It's only really in the last decade we've really gone out there. We've put monitoring stations in place in the major cities in New Zealand. We found out what our air quality is like. A lot of our South Island towns, as many people know, are polluted by wood smoke in the winter. In Auckland and to some degree in Wellington, we have a lot of traffic, and the traffic just keeps on growing and growing and growing.
So what are the more dangerous air pollutants? The World Health Organization has come up with a list of the most harmful to human health, known as the Dirty Five. Carbon monoxide, an odourless gas that reduces the oxygen carrying capacity of the blood and can affect sensitive organs like the brain and the heart. Nitrogen dioxide. It appears to have an inflammatory effect on the lungs and can be especially harmful to young children, asthmatics, bronchitis sufferers and the elderly. Sulfur dioxide, a potent respiratory irritant. Levels keep rising due to the increased number of diesel vehicles on our roads. Ozone. In the stratosphere, it's a useful blocker of UV radiation, but at ground level, it's an air pollutant and it impacts on the respiratory tract. Particulates, tiny airborne particles that come from both natural and man-made sources, like car emissions, wood burning, and aerosols. NIWA's project aims to find out just how much of these Dirty Five we take in every day. Most people assume that in one area, people get exposed to similar levels of pollution, but that's not always the case.
The conventional expectation is that there isn't a great deal of difference between one person's air quality and their neighbour's air quality. They both live in the same part of town. You'd expect that they're exposed to the same kind of pollution. Generally, what we've found, though, is that the differences in the exposure between one person and their neighbour can be enormous. One of the most important factors is the way they move around the city. The whole assumption that your air quality is to do where you live with assumes that you stay at home all day, but you don't, you travel.
It's only recently that many measuring instruments have been small enough that you could carry them on a person. Now, we don't spend all our time stood next to an outdoor air quality monitoring station, so it's important to follow a person through their day to understand how they are exposed to different levels of pollution in the different places they go.
With new portable instruments, they could finally take scientists out of the lab and onto the city streets. They put 3 scientists simultaneously on 3 very different modes of travel: by bicycle, by bus, and by train. I got the bicycle. It must be the healthy option. Or do the other 2 know something that I don't?
We're all heading out at the same time during peak hours. We're starting in the mornings, so we're traveling on the same route. So we can actually compare how much pollution you're being exposed to when you're taking different commuting modes.
So what we have is we have a CPC, it's a 3007, the condensation particulate counter. Every second it just counts the number of particles. We have a grim, which that actually gives a weight measurement of particulates. This is a Q track here, which will give a CO and CO2. We also have on the front a Langen, which is electrochemical cell, and that will actually give a CO reading. We have a GPS and also a camera on here. So if there is a bump in the data, maybe that we've gone through a plume of air, which is actually showing up on our data, we can actually figure back and we can look at the moment in time where we were and when it occurred.
In terms of carbon monoxide, it's not very polluting, the trains, because it runs away from your normal traffic out on the roads and runs on its own track. But there's a lot of self-polluting happening, especially if you're close to the carriage and there's the diesel emissions directly at you. So you get a lot of particulate pollution from that. And in terms of health, particulates is one of the main causes of respiratory diseases.
Doing this kind of test, I find myself really aware of the fumes that I'm breathing in. But with the density of Auckland's traffic, sometimes air pollution is the least of a cyclist's problems.
So, John, this is the trace of your journey today. So all those peaks are you going through the plume of a car as you ride by it.
So this could be a bus, a car.
Something like that. And once we've looked at the photographs and followed the GPS track, we'll be able to follow your journey and say that spike's that bus. These big spikes could be intersections, because intersections tend to be the most polluted areas on a road.
What we found is when we really started looking at this travelling data, we found that the highest exposures were in the car, higher than being on a bike on the same road. So the cyclist is right behind a huge dirty bus. There's a big cloud of diesel smoke, and what happens is, within a second, the wind's blown it away. If you're behind that same dirty bus in a car, that dirty air gets in through the vents and it's trapped. It takes several minutes for that air to escape and recirculate from the car.
Air pollution is an issue that affects all of us, but there's still so much we don't know yet about what air pollutants are doing inside our bodies, especially the effects that particulates are having on our bodies at a cellular levels. Let's meet Joe Kavanagh from Landcare Canterbury, one of only a handful of scientists internationally working on the biological responses associated with particulate emissions.
My research is unique in New Zealand. There's basically only us doing it, which is quite cool. We're interested in what's the relevance of particle composition and particle size to the effects that are being observed.
Particulates are particles in the air so small that they can't be seen with the naked eye. However, when inhaled, they can attack the body at a cellular level. They are often lumped into one category, PM10, which refers to particulates of 10 microns or smaller. What Joe is doing is examining whether changes in particulate sizes have different health effects on human cells.
Air quality tends to be regulated on a size and a mass basis, and the implications of this is if you just regulate things on a mass basis, you may be missing what's actually important in terms of the biological effects.
This beast here is a size fractionation cascade sampler, one of only 10 in the world. It basically sorts out and filters the different airborne particulates according to their size.
It enables us to give a better characterisation of the particles and therefore what components contribute most to the toxicity.
But it's not just the particulates that are dangerous. Other harmful compounds can piggyback onto the particles, making them even more toxic when inhaled. Polycyclic aromatic hydrocarbons, or PAH, are a group of contaminants that Joe is testing. They are mutagenic, which means they can cause cells in your body to mutate and become cancerous. In New Zealand, the PAH concentrations are very high, especially in wood-burning cities. This makes Joe's research crucial in finding out how they affect our health.
The ones which we're looking at are around mutagenicity is a key one. That's the first step in getting cancer forming, basically. The response that we're measuring here is how much mutation of that cell line occurs, and that's what results in the colour change. We've done some work on ambient air sampling in Christchurch and Auckland, and what we found is that even though Auckland has got lower particulate concentrations than Christchurch, some of the inflammatory responses in particular relatively speaking, a lot higher.
It's still too early for Jo to draw conclusive results, but what does she expect to uncover about the health effects associated with the different particulate sizes?
Expect what we'll see is more of the cancer types of responses and different types of inflammatory responses we'll see with those smaller size fractions.
So Jo's research is well underway to showing us the effects that air pollutants have on our bodies and helping us to understand the very real dangers of particulate pollutants. But what do we have to fight against air pollution? Let's meet a scientist who's working to further our knowledge of the oldest and best known cleaner of the air, the trees. Now, why do you study trees? Why are trees important to us?
They have all these wonderful properties in that, they take in carbon dioxide from the air, put out oxygen, which we breathe, regulating water in the environment, but also they're able to take quite a lot of pollutants, like some of the car exhaust gases, out of the atmosphere, and they absorb them. The main interest at the moment is in their ability to what's called sequester carbon. That's what the whole Kyoto Protocol is about, after all. People want to know, well, how much carbon do trees absorb? 30% of a tree is carbon, and that's where all the carbon dioxide goes. Wood also has got oxygen, hydrogen, nitrogen in it, but a large part of it is carbon. What happens is we cut pieces off it and then analyse the carbon that's actually in here, actually measure it, work out its age. You can see from the tree rings here, and then we can work out how much carbon per year a tree accumulates.
What's unique about your research, Neil?
I think we're one of the few places in the world that have been able to analyse whole trees. We are really fortunate. We were given 20. We then bring it into the lab here. In the field, we actually put them through a commercial chipper, and you end up with material like this. And then we've got to put them in the oven to dry them to get them down to a standardised weight. Then we've got to reduce it down to a fine powder. So put it through this grinder, which is essentially like a very powerful home food processor. So I can introduce you to Luke Gart, who will run you through how we actually do the final steps and find out how much carbon was actually in the wood.
The material is combusted. The organic material is released as a gas, as CO2. The CO2 gas is then moved on through a detector. It's based on infrared. So based on the amount of sample plus the signal I get from the detector, the carbon concentration can be estimated.
In New Zealand, at least, it's probably the first piece of work that's looking at the native trees. I think this is one of those few examples where we're actually going to get a full analysis of native tree carbon content.
Right, so what does that mean for us? What does that mean for New Zealand?
The Kyoto Protocol that was negotiated was originally just based on pine plantations and the amount of carbon dioxide that pine would take out of the atmosphere compared to how much we emit over our Kyoto allowance. Native systems weren't included, and native forests cover millions of hectares of the country, many times more than pine plantations. The important thing about native trees is that they're there for 1,000 years, maybe, in the case of a kauri. If we just relied on pine plantation, they're logged every 25, 35 years, whereas what we're talking about with native forests is a long-term taking carbon out of the atmosphere.
Trees are a fantastic resource for cleaning up our air, but we still need to directly address the air pollution that we're creating. Products do exist that purify vehicle emissions by removing toxic gases, but these are really expensive and not very efficient. What if we could develop a system that increased that efficiency at removing toxic gases while minimising the cost to the user? Let me introduce you to a Kiwi scientist who's helping to develop just such a system. If you've watched this program before, then you already know him. My name's John Watt. I've recently completed my PhD at nanotechnology at Victoria University in Wellington. Nanotechnology is the study of the very, very, very tiny. A nanoparticle is 50 to 100,000 times smaller than the width of a human hair. That's like comparing a basketball to the diameter of the Earth. And when you get down to this tiny length scale, we see a whole lot of unique and unexpected properties. So you can think of it like if you had a lump of sugar and you put that in your coffee, it would take a long time to dissolve. But if you mash that up into a powder form, you get a very, very large surface area, and that dissolution happens a lot faster. So the same kind of thing happens on the nanoscale, where you get a very, very large increase in surface area, and the surface becomes very important in determining the properties of the system. My research into nanotechnology has helped enhance the properties of palladium, a rare metal used in catalytic converters, which are responsible for removing toxic gases from vehicle exhausts. Here's how it works. Toxic gas from the engine enters the catalytic converter. The gas lands on the palladium where it undergoes a chemical reaction to turn it into something more environmentally friendly. There's a lot of different sources of pollution, but this is one of the biggest, the personal car. Let's have a closer look to see what's coming out of the back of it. Now we've got the probe in the exhaust, we come to the computer here and it shows up the usual suspects in our vehicle emissions. We've got carbon dioxide, hydrocarbons, nitrous oxides, carbon monoxide. Well, that was a modern car, not so bad. Quite a bit of carbon dioxide, but only a small amount of carbon monoxide and trace elements of nitrous oxides. But let's have a look at an older car, which is a much more common sight on New Zealand streets. The one we looked at before was modern and had a catalytic converter. This one doesn't. So let's see what the emissions are like now without a catalytic converter. As expected, the emissions are far greater than with the modern car. We've got an increase in carbon monoxide and we've got an increase in unburnt hydrocarbons. The palladium in catalytic converters does do its job, but there's two problems. It can get easily blocked up and palladium costs a small fortune, almost 20,000 New Zealand dollars per kilo. So what we're looking to do is use palladium on the nanoscale, which will increase that activity of the catalyst while minimising the amount of metal used, so that reduces the cost. So how do we make these palladium nanoparticles? Time to don the lab coat and get the chemistry flowing. So I guess one of the main things in growing palladium nanoparticles is you need a palladium source, and our palladium source is a palladium salt. But to make palladium metal, we need to reduce the salt into a metallic form. Now to the palladium salt, we're going to add what's called a surfactant. So this is like a soap molecule. And this is what we use to control the growth of the nanoparticle. So without the surfactant, we'd just get a large crystal of palladium. The last thing to chuck in is a solvent. So this is the solution that the reaction takes place in. We then use what's called a Fisher-Porter bottle to do our reaction. And using this, we can put any type of gas we want in there at any type of pressure. Now I need to fill the pressure reaction vessel with hydrogen gas, which acts as a reductant. It's time to stick it in the oven at about 80 degrees, and that's going to kick off the reaction. It's a tricky reaction to control, so let's hope the conditions are just right to give us the results we expect. This is what palladium looks like up close as it grows into a nanoparticle. The surfactants we add force the nanoparticles to branch out in all directions, leading to a complex shape. So now we've grown our nanoparticles, we need to make sure that we've got the size and the shape that we want. But we can't just look at them because nanoparticles are so tiny that they're much, much smaller than the wavelength of visible light. So that's about 5 millimeter across. And when that solvent dries, there's going to be up to 1 trillion nanoparticles on that copper grid. What we need to use is this beast here. This is the electron microscope, sponsored by the McDermott Institute and worth $1.2 million. So this gives us really, really high definition structural information about the nanocrystal. The whole electron microscope is under a super high vacuum, and this is because we're using electrons to image. If there's any dust particles or air molecules in there, the electrons will scatter off that and we won't be able to get a picture. To make sure we've got a complete vacuum, we need to add liquid nitrogen, and this creates what's called a cold trap. So now we can look at an electron micrograph of what we've made. Because we're using electrons to image, we can get right down into the structure of the nanocrystal. So each one of these spheres here represents an atom, and we can see that it's all arranged in a uniform structure to give us our palladium crystal. These are palladium nanoparticles as we expect them to grow. So these are those symmetrical, spherical or cubic-like shapes. But these aren't that interesting for catalysis because they've got a very low surface area. But what we've been able to make are these high surface area sea urchin-like particles. It means there's a very, very large surface area for those toxic gases to land on and undergo their chemical reaction. So this means that you get a much higher activity, but you can use a much smaller amount of metal, so it reduces cost. There's over 700 million cars in the world, and each one of these can produce up to 300 kilograms of toxic gases every year. So there's a lot of potential for this technology to purify those emissions and make cleaner air for everyone. That's all the time we've got to explore in this show. We'll see you again next time.